David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember that you can adjust the playback speed as you desire. Second, you can pause the video at any point to jot down notes or write down questions. Third, you can turn on the captions so you can read my words on the screen. Let's review our chapter on exponents and logarithms. For students in my class, this was chapter 9 out of our IB textbook. And let's just go over some high spots. I'm going to summarize the things that we did, and then we're going to do 2 or 3 problems at the end that kind of pull it all together into an IB style type question. So let's get started. So the first thing we did, we had a bunch of laws. So we started off with just reviewing the laws of exponents, how you can manipulate exponents, multiply, divide, add, subtract, all of those kinds of things. And we did a couple little exercises on that. All of that should be review for you because it's covered in a prior class and it's assumed prior knowledge for this class, but we did spend some time there. The second thing we did is we changed between exponents and logarithms. So there was one fundamental equation that let you change an exponential equation where the variable was in the exponent into a log equation where you could use your calculator to solve for that variable. So that was one of the key parts of bouncing around between exponents and logs. And then finally, in terms of laws, we got a bunch of rules where we could manipulate logarithmic expressions and we could simplify them. And this was one of those places where equivalent answers have to be simplified all the way down as far as they go. And we had some fairly complex expressions that actually simplified down to, say, 2 or 3. So when you're doing those problems, you need to simplify as far as you can. Next, we looked at exponential functions, and they have the form f of x equals some constant outside the base, which could be a number, and the exponent, which has the variable. Now, this can be more complicated than just x, but basically your variable is in your exponent, and then after that you have plus some constant. And we can derive a bunch of things from the equation itself. The y-intercept is always going to be the point 0, k plus c. So that's a coordinate where the graph crosses the y-axis. And then the horizontal asymptote of this function is always going to happen at, it's going to be the line y equals c, that horizontal line. So let's look at logarithmic functions and their forms. So what we have here is f of x equals log some base a of x minus h plus k. And you start to see these forms are really familiar and similar across function types. So in this case, the x-intercept is not so clear. It happens when the whole expression is equal to 0. That's the x value for the x-intercept. So I put here f of x equals 0. Whatever number that is, that's going to be the x-coordinate of the x-intercept. And of course, the y-coordinate is 0. So I can't be really more specific in this case. The vertical asymptote is just x equals h. It's a vertical line at h, and you remember that the minus sign is part of the form. So if it's minus 3, the vertical asymptote is x equals 3. All right, after that, what we did is we solved exponential and logarithmic functions. And these operations and these lessons required that you know all the stuff that we've been doing in the chapter. It's very much a building enterprise going through chapter 9. And so you're going to need to manipulate these expressions with all the laws that we've had. You're going to need to tap into what you know about exponent rules, about log laws, all those things are going to come in handy at various little points during the manipulation, during the solving. We did this change base rule where we could change logs of any base to another base, and primarily that was so that we could use a calculator that could only do natural logs and base 10 logs. We also took the log of both sides. So we can take the log of both sides to simplify an equation to then solve it. Now, the thing about some of these techniques is that you didn't need them if you had the calculator. If you could just turn the expression into a log equation, didn't matter what the base was, you could just use the calculator and solve it. So there you have to pay attention to the prompts or the situation because it might require that you use this technique or this technique. Otherwise, some of these things were extra activities and ways to test your understandings of how to manipulate logs, but they were definitely the longer way around. Now, here's where you might need all these things. Any of these questions could be with or without the calculator. Obviously, solving the without the calculator ones should be ones that are kind of nice and easy, like 2 to the x equals 8. What's x? Well, has to be 3 because 2 to the third is 8. So that you could do in your mind because 8 is a power of 2. So some of these will be set up so that as you simplify them on down, you can suddenly see, oh, that's easy. I can tell what x is. So be ready to identify those and do those if you're on a non-calculator portion of an assessment. Same thing with some of these rules where you could use a calculator and solve it quickly. You might have a prompt that says, in terms of something, solve. In which case, you wouldn't have a calculator for that, and you need to use one of these laws to do that. So let's do some problems. Okay, this problem is a typical IB problem that uses one topic to set up work in another topic. So the prompt for this is as follows. Here's our function, has horizontal tangents at A and B. Find the x coordinates. So understanding this prompt is from our chapter on differential calculus. And you need to understand what this prompt means in terms of that chapter so you know what to do with our current chapter and this function. So we have an exponential function with e in it, and presumably it has a graph that has horizontal tangents somewhere. And so this prompt is about using a derivative to find those points. And so you have to remember a horizontal tangent line means the function has a maximum or a minimum because the tangent line is tangent to one point. So at a maximum or a minimum, the tangent is exactly flat. It's horizontal or its slope is 0. So quick overview. What we did with differential calculus is we took the first derivative of our function, set it equal to 0, and solved it. And that gave us the x-coordinates of any horizontal tangent points on the original function. So let's take a quick look at this graph and then we'll get to work. Okay, here is a rough sketch of the graph. When we get done with this problem, I'm going to take you over to Desmos and we'll take a look at the graph in that tool. But it roughly looks like this. And you can see I have a minimum there and I have a maximum there. So what this problem is asking for is to find the x-coordinates here. This could be our A, and that could be our B. So we're trying to find the x-coordinates of these points of the minimum and the maximum because at that point, my tangent lines are horizontal. And so again, what we're going to do from our chapter on differential calculus is we're going to find the first derivative of this function, set it equal to 0, solve for x, and that should give us two solutions that will be these x-coordinates, these A and that B. So let's do that. So first off, you got to take a look at our function here. There's actually a fair amount going on. The first big piece to see is that we've got 4x times e to the 1 minus x squared. So we have a product rule situation where we have this function times this function. Additionally, this function is a chain rule situation. So there's going to be a bunch of things to keep track of here. So let's get started. First, here's my first function. I'm going to call that u. So I know that u equals 4x. Now, u prime is the derivative of u. So this is pretty easy. The derivative of 4x is just 4. Okay, so we're halfway there. Now we need to find our v and our v prime. So here's our v, just bring it on down. That's the e to the 1 minus x squared. So that's e to the 1 minus x squared. So there's our v, and now the v prime is going to be, now chain rule with an exponential function. Here's how I do it. It's a little cookbooky, but it's straightforward, and I think you can remember that. I'm just going to take the derivative of the exponential part, that's the part that's in the exponent. I'm going to take that derivative and then multiply it by the whole thing. That's how you use the chain rule. So 1 minus x squared, the derivative of that is just minus 2x. So this is minus 2x, and then times the whole thing. So that's times e to the 1 minus x squared. So now I'm set up for the plug-in step for my product rule for differentiating a product, okay? So if you're feeling bold, actually, let me do this. Here is what it's going to be. It's going to be u prime times v plus v prime times u. So that's what you're going to do to figure out the derivative of this function. So pause the video and do the plug-in step using this pattern with these little mini functions. Okay, here's my plug-in step. I did my u prime, which is 4, times my v, which is my 1, or my e to the 1 minus x squared. And then I added my v prime, which is minus 2x times this e exponential. So I have minus 2x times e to the 1 minus x squared times my u, which is 4x. So this is the derivative. Now when we did derivatives, we invoked basically the equivalent answer rule where this was correct, even if you could simplify it further. However, this time we need to set this equal to 0 and solve it. This form is going to be a little hard to do that. So what we're going to do is we're going to play around and rearrange this. And I want to take a look here. First thing, I have a plus minus, so I can just get rid of that. And this is really just minus. So I have one thing minus another. Hard to solve setting to 0. So what we've done in the past, here let me put my equals 0. What we've done in the past is we find a way to factor this expression so we end up with one thing times another. And then that we can solve by setting things equal to 0. So take a good look at that. And there is some factoring that you can do. Take a greatest common factor out of both these terms and write what's left in parentheses and come back. Okay, so the greatest common factor is actually one of the terms. Here is the first term, 4e to the 1 minus x squared. That is in here. I have a 4 there, and then here's my exponential term. So I factored a 4e to the 1 minus x squared out of both sides. So here that is. Now I have a 1 to represent this guy, and then what's left in this term is a 2x and one more x over there. So it's 1 minus 2x squared. So stop right now if you don't see how that worked. Make sure that that makes sense to you. Okay, so I just made some room so we can finish this up. Here's what we had on that last board down here. I have my first term, my 4e to the 1 minus x squared. That's my first term. And here's my second term, 1 minus 2x squared. When these are multiplied, they equal 0. That gets us our horizontal tangent lines and helps us find our A and our B from our original prompt. So what we do at this point is we set each side equal to 0 and we solve. So let's take a look at this first one. What value of x makes this equal to 0? Now I really want you to pause the video and see if you can figure out what value of x does that. Okay, if you came up with there's no value of x, you're right, because x is here, okay? So if x is 0, we have 1. If x is 1, we have a 0 power, but e to the 0 power is 1. So in fact, no matter what power we have there, we're going to have some value when we raise e to it. Then we're going to multiply that by 4, but it doesn't matter. There's no way that that can be 0. So there's no solution here. Okay? Well, that took care of what could have been a complicated problem. Now let's check this out. I have 1 minus 2x squared equals 0. Now, hopefully you can just go ahead, pause the video, and solve that on down and get our solution. Okay, so check this out. I just moved my minus 2x squared over to the other side, divided through by 2, got a half, took the square root, and I get plus or minus 1 over root 2. Now, some places we don't like roots in the bottom, so I just rationalize the denominator, which means get it out of the bottom, and I have root 2 over 2. And so that's our answer. And I have a plus minus, so that's good because I'm supposed to have 2. Now let's take a look at the sketch of the graph. So over here, this one is the minus root 2 over 2, and this one is the root 2 over 2. So this all kind of lines up, and this is one of those places where the IB makes problems challenging because they'll use one chapter's understanding to set up work from another chapter. or one topic's understanding to set up a problem that uses another topic's techniques and laws and theorems and so on. So you really have to understand how all of this stuff can be made to work together. And I think in some ways, that's like one of the biggest challenges for doing well on IB problems on IB tests. So let's take a quick look at Desmos so we can confirm our answers and take a look at what a nicely done graph actually looks like. Okay, here we are over in Desmos, and I've gone ahead and typed in my function over here. I have my f of x equals 4x e to the 1 minus x squared over here. And let me go ahead and just turn on the graph. I'm just going to click my little spot there. And you can see there's a very accurate version of that graph that I drew for you on the board just a minute ago. Now, check this out. I'm going to come right up to this maximum and check it out. The x-coordinate is 0.70711. And if you did this on your calculator, if you did root 2 divided by 2, you're going to get exactly that. That's the decimal equivalent of that is 0.707. So we've confirmed on the graph exactly what we just did with algebra on the board. Now, the board problem is a typical paper 1 problem. So that means the expectation is you would do that one without your calculator. However, if it was a calculator problem, then you would do this. You would just put the function in your calculator, find the maximum and the minimum. See, we have one down here, and that one's negative 0.707. Same thing, but it's just minus root 2 over 2. Let's do this one. So here's our function. G of x equals e to the 6x plus 3. Now here's our prompt. What does that mean? Do you remember what the -1 stands for? And not just here, in a bunch of other places in mathematics. If you recall, that's the inverse function. So this is saying, this prompt is asking us to find the inverse function for this one. Now there's a basic trick that we used when we talked about finding inverse functions. And that trick was switch x and y and solve for y. And so before I release you to just do that plug-in step, remember that this can be y. So this function could be written as y equals e to the 6x plus 3. So your first step here is to switch x and y and write that down. So go ahead and do that. Okay, pretty straightforward. I just put my x where my y was, and I put my y where my x was. So here is my function rearranged. Now I have this challenge. I have y. It's up here in this complex exponential part of this exponential side of my equation. Now, fortunately, there's a really easy way to make that simple. And if you remember something about having e to a power, something you can do that just simplifies that really quick, you'll be on the right path. So give that a think, try it, and come back. I want to remind you of a trick we learned a couple lessons ago. If I take the natural log of e to the x, that's saying log base e of e to the x, what that means is what power of e makes e to the x. So that's kind of like just write all in there. The power of e that makes e to the x is x. So ln, natural log of e to the x, is just x. So if we exploit this pattern, we know that we can take the natural log of both sides. So I have natural log of x equals, if I take the natural log of this, it's just going to be my 6y. So let's write it out. Natural log of e to the 6y plus 3. And that's asking the question that we just answered before. So that's just going to be 6y plus 3. So now I have the natural log of x equals 6y plus 3. And we can solve that, simplify on down with your basic equation solving techniques. So go ahead, pause the video and do that. I rewrote my equation, got the middle part out. So I have natural log of x equals 6y plus 3. Subtracted 3 from both sides, divided through by 6, and I get y equals the natural log of x, that's just ln, natural log of x minus 3 over 6. So there is my inverse function. G inverse of x is that. Okay, let's take this problem and add a wrinkle to it. So I'm introducing a new function here. We have h of x is just twice the natural log of x. And then I brought my inverse function. This is g to the negative 1. The g inverse of x is the natural log of x minus 3 over 6. So here's the prompt. Find where this function equals that function. So go ahead, pause the video, do your first step for this one. Okay, so I just set the two functions equal to each other. I have twice the natural log of x equals natural log of x minus 3 over 6. Now, let's go ahead and solve this equation. So a lot of basic equation solving techniques are in play here. Go ahead and pause the video and do that and take it as far as you can get it. So what I did here is I just multiplied both sides by 6. I got 12 natural log x equals natural log x minus 3. I subtracted my natural log of x from both sides. I have 11. Natural log x equals 3. I divided through by 11, so I have the natural log of x equals 3 over 11. That's great, except to solve, we really need to know what x equals. So this last step, non-calculator, this last step is test your understanding of what this is asking, what this is, so that you can rearrange the equation to something that gets x by itself. So go ahead and give that a try. Okay, I rewrote the natural log of x here just as what it really is. That's log e, log base e of x equals minus 3 over 11. So now let's get conceptual here. This is what power of e makes x. And this is that power. So what we know then is that x equals e to the minus 3 over 11 power. And for a non-calculator portion of a test, this would be your answer. You wouldn't need to simplify it further, but it's definitely further simplified from that one because we do have x all by itself. Differentiation. Now that you've watched the video, take a moment to jot down additional notes, some questions for class, or a short summary of the lesson. You can also go back and re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.